Hello everybody. This is your practice problems video for sampling distributions of a sample mean. All right, so I've got two different practice problems for you in this video, so we're going to go ahead and jump into it. I realize that one of my headings is wrong here. I'm noticing a lot of things that I did incorrectly, either in the slides or in the notes throughout this section. Sorry about that. But this heading should say sampling distribution of a sample mean. Practice problems. Whoops. It happens. I'm just amazed that I haven't caught it up until now, but there it is. Okay, so let's go ahead and talk about this practice problem here. So in this problem, we're talking about the birth weight of babies in an area of the world. Okay, and they give us a little bit of information. So they tell us at birth, babies average 7.8 pounds with a standard deviation of 2.1 pounds. And then they say a random sample of 34 babies born to mothers living near a large factory that may be polluting the air and water show a mean birth weight of only 7.2 pounds. So the community is thinking it may be the pollution caused by this factory is lowering the birth weights of their children, right? Which I'm pretty sure this was adapted from real data from somewhere in the world, and I cannot remember where. But we're going to do a little bit of math to figure out if these people should be concerned about this pollution in this aspect, right? Obviously, we should all be concerned about pollution in all things, but that's neither here nor there. Okay, so a couple of things. Let's pick out and label what all of these things are. Okay, it'll make our lives a little bit easier. Okay, so they're saying at birth, babies average 7.8 pounds. So that is your population mean, mu. Okay, and then a standard deviation of 2.1. So that is your population standard deviation. We have a random sample of 34 babies. So 34 is your N. Okay, and then in that sample had a mean birth weight of 7.2. Okay, so 7.2 is your X bar. It's like your data point. Okay, so the first question is, what's the probability of a mother having a baby weighing 7.2 pounds or less if the distribution of baby weights is approximately normal? And by this, I mean the population distribution. Now, the key word in this question is this, the word A. Okay, so here, I'm not asking about a sample of babies. I'm asking about one baby from one mother. That means that this is not a sampling, right, distribution question. This is a sample distribution question, meaning it's just a regular old normal distribution question, okay, which is why I put think z-score there. Okay, so what we are attempting to calculate here is what's the probability. Let me go back to what we're trying to find here is what's the probability that just X, not X bar, right, not an average, just one baby, right, has a weight of less than 7.2 pounds. Okay, that's what we're trying to find. So in order to do that, we need to calculate our z-score. This is just a regular old throwback to Unit 3 normal distribution problem. Okay, so I have my data point, okay, 7.2, minus my population mean, 7.8, divided by my standard deviation, 2.1. Okay, so that value is negative 0.286 if you round. Okay, so go like this. Whoop, draw my big arrow here. Okay, so the probability that X is less than 7.2 is the same as the probability that Z is less than negative 0.286, right? So you can pull your answer from the Z table, right? And I have a shaded version of what this looks like here. But for the actual probability, I got that value from my calculator. Okay, so my final answer here was 0.388. So the probability of one mother having a baby weighing 7.2 pounds or less is about, if you round up, about 39%. Okay, which in itself is not really troubling, right? Like that's not really, like I'm not super concerned about that. Like that probability is not low enough to cause me a great deal of concern. Now, obviously, I did not draw the normal distribution part on the right side of your notes, but you can see it here on the left side where you have the mean in the middle. We have our X value here at 7.2, and then everything to the left is shaded, right? So you can see that covers a pretty large area. So if I'm asking you just about one mom having a baby that's 7.2 pounds or less, that probability is pretty high, or it's not low enough for me to be concerned or for me to have any suspicions. Okay. So I'd be okay if it was just one, right? The statistic says that's probably fine, right? But it's when we get into the sampling distribution part that we may come up with some issues, right? Or the math may show us that this actually is a problem, okay? So I'm telling you now that the distribution of weights of these babies is actually skewed to the left, right? So rather than the population being normally distributed, the population is skewed to the left. Okay, so what we're going to try to figure out now by working with our sampling distribution is having a sample mean this low of 7.2, is that concerning? Okay, so first thing that we need to do is check our three conditions. Okay, so just as a reminder for you, your three conditions are the randomness, okay, which that's true. Okay, they said it in the problem that this was a random sample, so you can literally just say simple random sample stated in problem. Okay, next condition is the 10% condition. Okay, so best thing to do here is do 10 times the sample size, which is 34, and ask yourself, is that less than the total population of babies? Right? And I'm going to say yes over time, right? So yes, reasonable to have more than 340 babies born over time. Okay. I need to make this a little bit smaller. 1 second. My text size is a little bit too big for the space that I have available. Okay, so then my last condition is success fail, right? Or remember, you may hear it called large counts. Okay, so here you either have to have a normal population, which we don't, they're telling us that the population is skewed, or the sample size must be greater than 30, which it is. Okay, so literally all you have to write is n equals 34, which is greater than or equal to 30. Okay, so we are all set with our conditions. Okay, all right. So next, now that we know we can effectively use our normal distribution tools in order to solve this problem, we're going to go ahead and find the mean and standard deviation of the sampling distribution. Okay, so as you recall, I'm hoping from the last video that the mean of the sampling distribution is equal to the population mean. which in this case is 7.8. Okay, which is exactly the same as what you did with the sample distribution in part A, right? With the throwback to unit 3. Okay, but what you'll see is that the standard deviation of the sampling distribution is different, okay? Because we have to take the standard deviation they gave us and divide by the square root of n. So here, that's 2.1, right? That's the standard deviation of the population divided by the square root of 34, which I have worked out for you. Whoops. I have worked out for you on the left side of the screen here, okay? So that value is 0.36, okay? So notice that the mean is the same from the sample to the sampling distribution, but the standard deviation is vastly different, okay? All right, which leads us into the next part of this, which is to draw the distribution of both the individual baby weights and the sampling distribution of baby weights, okay? So obviously you can see them both. Whoops, here. You can see them both on the left side of the screen. I'm going to do my best to draw them here on the right side of the screen. Okay, so the one on the left is your population or your sample distribution. The one on the right is your sampling distribution. Okay, so a lot of similarities here, right? Like I've kind of been talking about the entire time, right? That you have the mean in the middle that's the same for both of them. Pardon my terrible drawing here. Okay, but if you look at the scale, it's much different, right? 3 standard deviations out for the sample distribution goes to all the way down to 1.5 and all the way up to 14.1, right? And remember that each of these data points inside here is 1 baby weight. Okay, so each of these x's is 1 baby weight. Okay, whereas in the sampling distribution, because we have this standard deviation that's much smaller, the scale, even if you go 3 standard deviations out, right, to the left and to the right, your range is much smaller, right? It only goes to a low of about 6.7 and a high of about 8.9 if you round. Okay, so the scale is much different, right? Another thing that's different is that each of the data points inside here is a sample mean of baby weights. Okay, so each data point is a sample mean of baby weights. Where in all of the samples, n is equal to 34. Okay? Right? So this is a key distinction that they like to ask about on the AP test, right? The difference between these two things, because there are similarities, but obviously there's some big differences. And I'm hoping that just by seeing the scale of the x-axis at the bottom of each of these, I'm hoping that you can see how when we calculate the z-score and when we do the actual shading, that the probability that we get at the end is going to be very different. Okay. All right. So next step is to find our z-score and our probability. So I have it shaded for you, and I'm going to do it up here. Right. So we have 7.8 is our mean, 7.2. I'm going to put like right there approximately, and we're finding the probability that we get a sample mean at or below that value, okay? So my z-score here is my data point, 7.2, minus my mean, 7.8. Let's see if this is going to cooperate with me. Divided by, you see it written over here, completely written out as 2.1 divided by the square root of 34, but I'm going to write it in its decimal form since I already know what it is, the 0.36 that we did up here, okay? So that value is negative 1.67, right? A much different z-score than what we got when we were dealing with the sample distribution, okay? So here, what we are trying to find now is not the probability that x is less than 7.2, but rather the probability that the sample mean x bar is less than 7.2, okay? Which is equal to the probability that z is less than negative 1.67, right? So again, I got my final probability from my calculator. I used normal CDF, but you could also get it from the Z table. You would get approximately this same value. So that probability that I got when I plugged it into my calculator was 0.0478. Okay, so what this means is that if we pulled tons of different samples of baby weights in this particular area, right? Weighed them all, gathered all of their and averaged each sample together and got an average weight for each sample, that we would get a weight, an average weight in the samples that small, 7.2 or smaller, just by random chance about 5% of the time, or a little less than 5% of the time. That number is low enough to make me think that something fishy is going on, right? Because we're saying it's unlikely that this happened just by random chance. The probability that it happened by random chance is 4.78%, right? So because that probability is so small, then there's probably something else that is causing the value to be that low in that sample, right? So that makes me think in my community that, yeah, I should be concerned about this factory, right? That because it's so unlikely that this happened just by chance, that there's some other cause that we have to consider, right? And obviously in this problem, we think that that cause might be the pollution from this factory, okay? And that's the core idea of everything that we essentially are doing this semester, okay? Which is, can we get a probability low enough simply due to random chance that would cause us to be suspicious that that result did just occur by random chance, right? And if we can succeed in that, if we can get a probability that's low enough, then it raises our concerns or our suspicions that something else other than random chance and the natural randomness in the universe is causing that result. Okay. All right. So last part of this one is asking what's the cutoff for the bottom 10% of babies born. Okay, so here, if they're asking you about a bottom 10%, they're talking about the entire distribution. Okay, so not the sampling distribution, but rather the sample distribution. Okay, they're talking about the population here, essentially. Okay, so when I draw my picture, right, of my normal distribution, it's my sample distribution, where the mean is 7.8 and the standard deviation this time is 2.1. Okay, so if you recall, think way back, right, way back to Unit 3 when we did problems like this is like doing a normal distribution problem, but in reverse, where I'm giving you the 10% I'm giving you this probability, and we have to work backwards to figure out what the X value is, right? So on my drawing, I'm looking at the bottom 10%. So my shaded area right here is 0.1, right? That's my probability. And I'm trying to figure out what this value is, right? That's what I don't know, okay? So the first thing you have to do is figure out the Z value for the bottom 10%. And you can do that with a Z table, but I typically use the inverse normal command on my calculator when I'm doing problems like this, just because it's faster. And so when I did that, I got that the Z value associated with the bottom 10% of any distribution is negative 1.28. Okay, so now I need to plug that into my z-score formula. So remember, my z-score formula is z, which we have in this case, negative 1.28, equals my data point, x, which I don't know, minus my mean, which is 7.8, divided by my standard deviation, which is 2.1. Okay, remember, we're not dealing with the sampling distribution here. This is just the sample distribution, okay, right? Where each of these data points inside here is one baby, okay? So then you just have to use your algebra skills and work backwards, right, to solve for x, right? And when I did that, I got that x was 5.109 pounds. Okay, so that is the cutoff, the bottom cutoff for the bottom 10% of babies born in this population. Okay? All right, so I know that that problem was kind of long and involved, okay? But I'm hoping that that will help you try this other one on your own, okay? So I'm going to give you this one other problem here, but I do want you to take note that they tell you things a little bit differently here. Okay, so if we go through and look at this, we're talking about weight in an elevator. Okay, so the elevator, they say they limit to 16 people. There's a weight limit of 2,500 pounds. Okay, and then they're saying we can assume that the average weight of everyone is 150 pounds. Okay, so that's our population mean. Standard deviation is 27 pounds. Okay, so that is our population standard deviation. Okay, and then they're telling us that the distribution is approximately normal. Okay, and we're taking a random sample of 16 people. So that's N. Now, the one thing they did not tell you here was a data point. I don't know what X bar is. Okay, but we're trying to figure out what's the probability that a random sample will exceed the weight limit. Okay, so if the weight limit is 2,500 pounds, then each person would have to average a certain amount if we're going to fit 16 people in there. Okay, so that's my little hint to you, is to calculate X bar, you're going to have to do some division here with the total weight limit that they gave you. Okay, so pause this video, give this one a try, and then check back with me in just a moment to see how you did. All right, folks, so go ahead and check your answers against mine. So for part A, this just says describe the shape of the sampling distribution. Well, the population is normal, so the sampling distribution will be approximately normal. That's it. That's all you had to say for that one. Okay. Part B, right, goes through the whole problem, right? Like the whole process of doing a sampling distribution of means problem. Okay, we're trying to figure out what's the chance that a random sample of 16 people on the elevator will exceed the weight limit, okay, which is 2,500 pounds. Okay, so first I have to check my condition. So I have my randomness condition, which is stated in the problem. They do say that we took a random sample, okay? Second, I have my independence /10% rule. I wrote out the 10% rule on the right side, But you could use independence here and say, well, it's reasonable to say that one person's weight is not going to affect another person's weight. So each person that you pull, their weights will be independent of one another. So either one of those is reasonable. Okay. And then the third condition is success fail, or remember, you may hear it called large counts. Okay. The sample size here is 16, which is not greater than or equal to 30, which is a problem. But think back to the start, we do know that the population is approximately normal. So that means that the sample size or the sampling distribution will be approximately normal, even though the sample size is less than 30. Okay, which I wrote for you as a little note right here. Okay, that even though n is less than 30, it doesn't matter because the population is normal to begin with. Okay, all right, so then we have the mean and the standard deviation, which is worked out for you now both on the left and right side of the screen. So mean of the sampling distribution is just the population mean, which is 150. Okay, and then you had to calculate your new standard deviation, okay, by doing the population standard deviation divided by the square root of n. So when I did that, I got 6.75. Okay? And then the last step is to go through and actually draw the normal distribution and find the probability. Now, you may recall that before I had you pause the video and try this one on your own, that I told you they didn't tell you what X bar was. They didn't give you the average weight of each person on the elevator, okay? You had to figure that out for yourself. So if we're trying to figure out how likely it is that we get a load of people that exceeds the weight limit, the average weight of each person would be 2,500, which is the weight limit, divided by the number of people on the elevator, right? So when I did that, I got 156.25, right? So there may be some fluctuation, right? But we're saying that the average, right, for this group, if we're saying we don't really care like which person weighs more or less, we're just saying the average of all the people together would be 156.25 pounds. Okay, so I drew my picture, okay, where I have my mean and my standard deviation, and we're talking about exceeding the weight limit. So what I actually need to find is the probability that the average weight is more than 156.25 pounds, right? Because if that's true, then we're going to end up exceeding the weight limit. Any average above that multiplied by 16 will give you a number greater than 2,500. So that would exceed the weight limit. Okay, so obviously I did not do it on the slide over here, but oops, let me go back one. I didn't do it on the slide, but I did calculate the z-score for you on the right-hand side of the screen. So I got 0.926 when I calculated my z-score, okay? And then I have my probability under there, that what I'm trying to find is the probability that the sample mean is greater than 156.25 pounds, which is the same as the probability that z is greater than 0.926. Now, when you do these types of problems on the AP test, you don't have to write both of those. I just do for you all so that you can see the connection between the two. You could write one or the other. That would be fine, okay? So when I plugged all this into my calculator, I got 0.177. Now, one thing I want to note for you is that because this is a greater than probability, typically for me, I will use the calculator in order to figure that out. The only reason being that if you remember on the Z table, all of the probabilities that are given to you in the Z table are less than probabilities, right? So you would either have to find the probability associated with that z-score 0.926 and then subtract that number from 1 to get the greater than probability, because that's actually what you want, or you could look at the opposite meaning opposite sign version of that z value, so negative 0.926, and that would give you the probability, the greater than probability, right? Because the normal distribution is symmetric, right? So the area to the left of the negative version is equal to the area to the right of the positive version. If that makes sense. Okay. So that was a long walk to get to the probability that I got here for 16 people exceeding the weight limit is 17.7%. Okay. All right, then the last question on here is, what's the probability of randomly selecting a person on campus that weighs more than 156 pounds? And I made a note for you on there that said, make sure you have the right mean and standard deviation, because we are talking about one person, meaning this is not a sampling distribution, but we're dealing with the sample distribution. Okay, one person. Okay, so that means the standard deviation in particular that we used in the previous part of this problem is not the standard deviation you want to use. You want to go back to your original population standard deviation, which is 27 here. Okay, so I went through the whole process. Okay, on the right side of your screen, like you can see the z-score, right? I got my z-score, wrote out my probabilities, but my final answer was 0.412, right? So much less likely to get a sample of 16 people where the average is greater than 156, right? Than it is to get just one person on this university campus whose weight is more than 156 pounds. Okay. And all of that really stems from this standard deviation equation, right? Because the standard deviation of the sampling distribution is going to be much smaller than the standard deviation of the population. All right, you guys, so that is it for this video. On the very last page of your notes, you may notice there's just this summary right here. You don't have to like write anything on here. I just wanted to provide it for you at the end. It gives you your mean and standard deviation formulas and kind of walks you through the conditions, right, for sampling distribution of a mean. It talks to you again about the central limit theorem, right? Just as a reminder, lucky ducks, you do not have to memorize these formulas. They are given to you on the formula sheet on the AP test. You just have to know where to find them and, more importantly, when to use them. All right. So I will see you all in the next unit. Unless I do some practice problem videos, I may actually do one more video for you with a couple more just like mixed practice problems. So I guess I will see you in that video. All right. Bye, everybody.